Propagation training rule. There are two algorithms considered, that is perception rule and delta rule. One way to learn an acceptable weight vector is to begin with the random weights. That means initially we are considering the random weights. This process is repeated until the perception classifies all training examples correctly. Weights are modified at each step according to the perception training rule. So this is the weights, this is the derivative of weights plus the value, and this is the training rule. For each linear unit, the weight Wi and do, that is derivative plus the weight, is the new weight. Suppose the perception outputs -1, but when weight or the target or the expected output is +1. Suppose the perception is -1 and the expected is +1. To make the perception outputs +1, then the weights must be altered to increase the value. That means to get from -1 to +1 is got by changing the weights. That is x of ij equals 0.1 and eta equals 0.1, t is equal to 1 and o is -1. That is the obtained output is -1 and the expected output is 1 and the eta is equal to 0.1 and the x value is 0.8. And now derivative of w is got by eta into ed minus od into x value. So eta, this value is the learning rate. That means rate at which the program should run, the speed. It can be 0.1 to 0.2. It is between 0 to 1. 0.1, 0.2, 0.3 like this. So initially we have given initialized at 0.1. So derivative is 0.16. So every time the weight should be increased by 0.16. Now eta is the learning rate. The perception rule fails when the training example is not really linearly separable. So in the previous example we have discussed how linearly separable occurs. Then the delta rule is used overcome this problem if the training examples are not linearly separable. The key idea behind the delta rule is to use gradient descent, to which we search the hypothesis, space and possible weight vectors to find the weights that fits the training example. Linear unit corresponds to the first stage of the perception without the threshold. So this is the error equation. So E is equal to 1 by 2 sigma d belongs to d, td minus od whole square. So this is the hypothesis space, and the vertical line indicates the E value, how E value is increased, and this is the W0 over W0 and W1. And this is the representation of E. The E is increased here and the derivative of E is increased. This point specifies the derivative of E over the weight. Now let us understand the derivation of gradient descent rule. Descent represents dropping or falling, that means reduction. Gradient is when interpreted as a vector is a weight space. It is a gradient when interpreted as a vector in the weight space. The gradient specifies the direction that produces the steepest increase in E. So gradient is the steepest increase in E. So training error derived as training error. So it is 1 by 2 sigma d belong to d td minus od square, where d is a set of training examples. TD is a target output for the training example D. OD is the output, the linear unit for the training example D. The direction of the steepest descent along the error surface can be found by computing the derivative E with respect to the each vector, that is derivative of E of W. So derivative of E of W is differentiation of E of W naught into differentiation of E over W1. So and the total of this is derivative of E over weights. And this is the representation of this. Derivative of E over all the weights. That is derivative of E over all the weights. Derivative differentiation of E over all the weights. Differentiation of E over all the weights. So this gives the derivative of E over weights. And this is the gradient of E. Now, the negative of vector that is minus derivative of E of over weight gives the direction of the steepest decrease. Since the gradient specifies the direction if the steepest increase is E, then the gradient decrease is given by minus E of WV. So that is delta W of I. So this is the value delta, the derivative of W of I equals eta into derivative of E of W. So that is minus eta into differentiation of E over differentiation of W. So n is a positive constant, eta is a positive constant for width over W. Negative because it should move the weight vector in the direction of decreases E. This is the direction it is decreased. So E is decreased to the negative. So this is the error which is increased with delta E, and the decrease of it should be in the negative, that is negative of derivative of E. So that is why we have negative of derivative of E over W. W is the weight and E is the error, so then the negative of it. So derivative of E of W over the gradient decrease. This is the gradient increase and this is the gradient decrease. So we need to decrease the given weight and given error over using weights. And that is derivative minus derivative of E of W. It gives the direction of a steepest decrease. Now calculating. Derivative of W equals minus eta into d of E over d of W. So that can be given, E value is 1 over d belongs to d, TD minus OD square. So derivative of W minus eta into d of W is 1 by 2 sigma d belongs to d, that is TD minus OD square. Applying derivation. So derivative of Wi equals minus eta into d belongs to d, that is TD minus OD into TD derivative differentiation of TD minus OD over weight. Here differentiation of TD over differentiation of W equals 0, that is TD is independent of weight, it is 0. So this becomes, these two are independent, so this becomes 0. Now minus OD over differentiation of minus OD over differentiation of W. So this is OD is the calculated value. OD is a calculated, that means sigma of I is equal to 0 to n W of I into X of I. Now we represent this as a sum of ID. Now we replace this minus OD with sum of ID. So there is a function that is used to do it, that is ft of sum of ID over d of wi. So this differentiation of minus OD over differentiation of W 2 is got by differentiation of sum of ID over W of I. So now derivative of W equals minus eta into d of d is Td minus Od into differentiation of f of sum of Id over differentiation of W. So where Od is equal to transfer function Ft and it is applied to sum of the weights, and we get, so this is from calculus, differentiation f of g of x over differentiation of x can be represented by f of x differentiation of f over g of x into differentiation of g of x over differentiation of x. So this is replaced here, where for f of t sum of id it is f of t sum of id over differentiation of sum of id into the differentiation of sum of id over differentiation of wi. So these two cancels and it becomes 1. So into this sum of id over w of I. So differentiation of sum of id over wi equals this is sum of id is represented by this, and wherein the weight are independent, so remains is x of ij. So we get the unit, it is just simply x of ij. Now we place this the value eta into sigma d of belong to d belong to d, td minus od minus of differentiation of ft into sigma sum of id into over sum of id into this value, and we get 1 into minus differentiation of sum of id over w of I, and finally we get derivative of w of I equals this minus, and this minus is become positive, and this is plus into eta into d belong to d td minus od into star of x of I. Now gradient descent algorithm is written as initialize the derivative to 0 and then the input value, and for the each linear unit w of I, and this is the derivative we have calculated, and this is the for each unit weight w of I do w of I 2 plus derivative of I. Next one is stochastic approximation to gradient descent. Problems with gradient descent is that whenever there are many local minimum, that is many local solutions, and there is a possible lot of small errors, and so it takes it takes too many steps to find the steps in the gradient descent is needed. So that is one error, there is too many steps. And the error, if there are multiple local minima in error surface, then there is no guarantee that the procedure will find a global minimum. So this is what we have, there are multiple minimum and the error is more, finding the global minimum is difficult. So to solve one common variation on gradient descent is intended to solve these difficulties is by incremental gradient descent, that is stochastic gradient descent. So this is got w of I equals w of I is got by in gradient descent derivative of wi equals derivative of w plus eta into t of d minus over d into x of I. So this is E value is 1 by 2 sigma d belong to d td minus od square, that is E is calculated as once, it is once calculated, and that is gradient descent. But in stochastic gradient descent, so derivative of WF equals eta into TD in minus OD into X of I, that is just only this much. No derivative of WFI. And E value is no sigma is used, and individually each value is calculated. That means this becomes ED. So this becomes ED is not written here, so it becomes ED W of W. So that is equal to E is calculated for each samples. That is stochastic. So it is once it is calculated, and here it is calculated for each sample, and this is called delta rule. And this is one of the example for this. So artificial neural network. So the sigma W of I and sigma W of I into X of I. That is, these are the values, and we calculate the output, and this is the gradient descent. And thank you.